helped us to understand better massive astrophysical bodies as black holes and neutron stars, and can futurely be very handy for understanding cosmic early processes such as inflation. But beneath the detected sinus by LIGO and Virgo, you have weaker signals that cannot be resolved separately by the detectors. And so we have to combine them and study them as a stochastical gravitational wave background. We expect that LISA, the first detector, space-based detector, will be able to assess part of this background, mainly the part that comes from our Milky Way, the sources in our Milky Way. And so it is a topic that will be very important in a decade or so. And our goal here is to investigate whether this stochastic background can have corrections when we study modified theories like Horndeski. Okay, so usually when we talk about stochastic background, we try to relate the detected signal to the spectral energy density of gravitational waves by a function. And the reasons we think that this can change in modified theories are two. First, the propagation equation for gravitational waves in a cosmological background changes. Is corrected by a function. And the second reason is that the energy momentum tensor for the gravitational waves also change when expressed in terms of gravitational wave amplitude. And so this can change both sides of this equation in some way. So first, when dealing with gravitational wave spacetimes, we usually separate the metric into two parts. One part varies slowly and has a high amplitude, and the other varies more rapid and is very tiny. And this tiny part is the gravitational wave, and the rest we call the background. So we will work in this framework. So there's a famous theorem proved in the 70s, if I'm not mistaken, by Lovelock, in which he demonstrates that the most general Lagrangian, depending only on the metric, that gives second-order differential equations in 4 dimensions, is the Lagrangian of Einstein-Hilbert that gives general relativity. And so the simplest way for you to generalize general relativity is to add a new degree of freedom. And the simplest way of doing that is adding a scalar field. So an example of a scalar tensor theory is the Horndeski theory, in which you have several contributions, additional contributions, that depend on functions that are functions of the scalar field and the kinetic term related with this scalar field. General relativity is retrieved when we make G2, G3, and G5 equal to 0, and G4 equals to 1. And there is another theorem that proves that in 4 dimensions, the most general scalar tensor theory, the most general scalar tensor theory that gives second-order differential equations, assuming a non-degenerate Lagrangian, is the Horndeski theory. So has this form for the action, right? And by non-degenerate Lagrangian, I mean that when you define your canonical momenta, you can solve this equation 9 for the generalized velocities of your theory. So multi-messenger observations from binary neutron stars helped us to understand that the speed of propagation of gravitational waves is very close to that of light. at least for low redshifts. And this restrains the possible Horndeski theories which you can work on. And we call this restricted Horndeski theory reduced Horndeski. And the restriction is that the G5 function must be 0, and G4 only depends on the scalar field directly. And so the action of the Horndeski theory is just this equation 10, very much simpler than the other. We will work in this reduced Horndeski theory and try to calculate the signal detected by 2 different detectors. So before that, I need to talk about 2 simplifications we will make. The first one is that in general relativity, you have 2 degrees of freedom for the gravitational waves, the plus and cross polarization. They deform space-time transversely to the direction of propagation, gravitational waves. But in Horndeski theory, you have another mode that does the same thing, but longitudinally, so on the direction of propagation of gravitational waves. In geometrical optics approximation, this longitudinal mode does not contribute to the energy of gravitational waves and does not contribute to curvature as well. And so we will neglect this contribution, this mode here. The second point is that in the same way we split up the metric into a background metric and a high frequency metric part, here we could do the same thing to the scalar field. So we could split it on a background part and a high frequency part. And you can show using the equations of motion that the perturbation here, delta phi, obeys the wave equation, contributes to curvature, and carries energy. And so you can call this a scalar wave. But here, for simplicity, we'll neglect scalar waves as well. Regarding background evolution, we will assume we are in an isotropic homogeneous background universe. And so we will use the Robertson-Lemaitre metric. And the equations of Friedman equations generalized in this scheme are 12 and 13. So you can see they are very complicated. In general relativity, for an arbitrary background, you have an equation of motion for the tensorial perturbations that is given by equation 14. And if you particularize for the FLRW metric, you end up with the equation 15, which is only a wave equation with friction term that has to do with the expansion of the universe. When you go to the reduced Horndeski theories, this friction term is corrected by a term that depends on the G4 function. And so this is one of the reasons we believe that stochastic background can have a correction in these modified theories. The previous equation can be solved with a wave packet-like solution, but damped by a term that has to do with this A effective. That is simply the scale factor corrected by a square root of G4. And so we can plug in this solution into the equation that gives the gravitational wave energy density, that is equation 19. And you can see that you have a G4 factor here on front that would be 1 on general relativity. And so we can combine this G4 with the correction of equation 17. Okay. And so the angular brackets here, they stand for the so-called Brill-Hartree average that filters out high-frequency contributions to the function that is being averaged. It is a space-time average with a filtering function inside. So we will make some statistical assumptions about the stochastic background to simplify the analysis. First, we will assume that it is Gaussian, and this means that you can statistically describe it fully just analyzing the mean and the variance of the signal. We will assume that it is ergodic, and this means that the space-time average can be changed to an average on the random variables. And the random variables here will be the amplitudes of this wave packet. And so we can make this change. We will assume that the signal is statistically homogeneous. That means that the mean and the variance of the signals do not depend on the xi, the spatial coordinates. And we will assume that the signal is statistically unpolarized. And this means that there's no correlation between different polarizations. And so assuming everything, all of these things, we arrive at a two-point correlation function of the amplitudes of each polarization that have these delta functions and power spectrum in front. I would like to emphasize that here we are still assuming that the background can depend on direction of observation, this omega hat here. And this is important because the detector frame usually is not the same frame as the gravitational wave fluid. And so you may have anisotropies coming from Doppler booster effects when you go from one reference frame to the other. And so we can make the average using these assumptions. We can arrive at the spectral energy density of gravitational waves that have this form, and there are two key elements here. The first is that it behaves as a function of the scale factor with the fourth power, as we would expect, since we are speaking about radiation fluid, right? It propagates with the velocity of light. And the other thing is that it is corrected by this Q of Ti function here that has to do with the ratio between the fields in the modified theory when compared with general relativity. But this is something that depends on your choice of initial condition. And so if you want your modified theory to retrieve general relativity at some constant time hypersurface, this Q of Ti is 1, and you obtain the same expression you would in general relativity. Remembering that the scale factor will change because the equations of motion, the background equations of motion are different. And so, but the functional dependence is still the same. So even though the propagation equation changes and the energy momentum tensor of gravitational waves change, you arrive at the same spectral energy density for gravitational waves, functionally. So now I will analyze the signal. So each detector has a signal that can be split up into the strain that gravitational waves make on free particles, and a part that has to do with the noise. And what we usually do is we take two signals measured from different detectors, and we correlate them in a given window, time window, that is this capital T. And we assume that the noises are uncorrelated because we are picking up different detectors localized at different points of Earth or space. And so the signal is simply the correlation between the strains of the two detectors. And then we can substitute the wave packet solution we got previously on this expression, 24, and we arrive at this expression. And here the correction when compared to general relativity would be this G4 function inside this temporal integral. Okay, so, but the point is that the capital T here, the time window that we are detecting gravitational signal is of order of 10 years. And so compared with the background evolution, we can assume that all the background fields are approximately constant. And so this integral can be done. And we arrive at this final expression, in which we still have the function G4, but evaluated today. Okay. So this would be possible correction to the signal, but really it depends on your initial condition, the initial condition you want to give to your background universe. If you want your theory to retrieve general relativity for high redshifts, then you have to impose that the fields are the same as general relativity for this high redshift zone. And you would have to use the generalized Friedmann equations to obtain the field today. Okay, right. To obtain the fields today. And so this would give a non-trivial correction to the G4 factor there. But if you want the general relativity to be retrieved today, then this G4 factor is only 1. But then you would have, in principle, high redshift cosmology different from the one predicted by general relativity. So you have to decide which initial condition you want to give. So that's it. So concluding, assuming some statistical properties for the stochastic background, we concluded that the spectral energy density has the same expression when written in terms of the scale factor, provided that we give an initial condition coincidence to the general relativity theory. And we concluded that we can have a correction to the stochastic signal if we assume certain initial conditions for the background fields. What we could do to generalize further this result would be to assume that scalar waves are present. In this case, we are almost certain that the energy momentum tensor will have another contribution. So here you have the energy momentum tensor of gravitational waves for a Brunnsdyk theory, that is a scalar tensor theory, a particular case of Horndeski theory, in which you arrive at a correction to the energy momentum tensor that gives corrections to the energy and furthermore the signal of stochastic background. And so we would like to investigate further how does this, what kind of corrections you would have assuming a reduced Horndeski theory. For this, we would have to take the action of the theory, expand it to second order in the amplitudes of gravitational waves, and use the averaging scheme to arrive at the general energy momentum tensor expression in terms of the tensorial and scalar parts of the theory. And that's it. Thank you.